Flipped classroom video for further maths unit 2, regression line. Consider two variables x and y which are known to be linearly related. We can write the relationship in the form y is alpha plus beta x. Think of y equals mx plus c, where c is our alpha, would be our y-intercept, and beta would be the gradient. Where we start from would be the alpha. By observation, we get the following plot of data with accurate x values. So we set the x values and we observe the y values. We can draw a line of best fit through the data to estimate the true relationship. The line would be drawn in the direction of the crosses so that the points lie fairly evenly on both sides, and usually through the mean of the x's and the y's. The linear regression attempts to model the relationship between two variables by fitting a linear equation to the observed data. Now, the method of least squares is the one we are going to use. So the dots are the observed data. The d, so from each xi, yi, the d I is the difference between the vertical difference between the point that was observed and the true relationship. Suppose that is the true relationship. So we need to calculate the least squares estimates of a and b for alpha and beta. We need to minimize the sum of the squares of the vertical deviations, so these d's, from the true line. And because we could be above or below, we're going to minimize d squared so that there are no negative values. So d squared is what we're interested in. Then the estimated regression line will have the equation y equals a plus bx, where a and b are the least squared estimates for alpha and beta. Using the same summary measures that we used in the video on correlation, i.e., so sxx would be either that one or the sum of x squared minus the sum of x all squared over n. Similarly, syy and sxy are those combinations, and we're going to use those. So let's prove one of them. So d is the difference between the true value and our estimated value of ya plus bx. So we're going to square that value. So the minus, it becomes a minus bx. So we're going to square that and then we're going to add them all up. So s is the sum of the deviations squared, which is the y minus a minus bx all squared, the sum of all those. We're going to take b first of all as fixed. So we're going to differentiate the s with a. So we're going to differentiate the a in here. So we've got a bracket squared. So it's twice the bracket to the power 1 times the differential of the minus a. So the differential of minus a is minus 1. So we can take the minus to the front. So it's twice minus 2 times the sum. Well, I can take the sigma in, so sum of y, and if I'm adding, a is isn't summed, so a is just there each time, so I'm adding that n times, so I've got na, and then minus b times sigma x. I've taken the sigma in there. Now, I need to minimize, so I'm going to put that equal to 0. So I can divide by the minus 2, so that can go because it's equal to 0. Then take the na to one side. Then I've got that is equal to sigma y minus b times sigma x. If I divide by n, I've got a is sigma y over n minus b is sigma x over n. And sigma y over n is the mean of the y, and sigma x over n is the mean of y. So my A is equal to y bar minus b x bar. So we are going through the mean of the x's and the y's. So that's the equation I've got for A. If I substitute that back into this equation for S, so instead of A, I've got y bar minus b x bar. If I collect terms, so I go y minus y bar minus b, and then I've got plus x, so that's minus minus, so minus x bar in there. So within the bracket, I got y minus y bar minus b x minus x bar, and then square all that, and then sum the answer. Now if I differentiate with respect to b, as I've removed my a, so if I differentiate respect to b, that is the differential, that's the coefficient of b. So it's twice the bracket to the power 1 times the differential of the minus b, or the differential of the inside of the bracket. So it's going to be minus x bar. I can put that in the front and multiply through. So I've got x minus x bar times y minus y bar minus b and x minus x bar all squared. Therefore, putting that equal to 0, I can multiply through by, or divide through by minus 2 and get rid of that, putting it equal to 0. So I've got b x minus x bar all squared is equal to x minus x bar y minus y bar. Divide that, and that is one of the summary measures that I'm supposed to have. So my b is now equal to the sum, the s of xy, which is, I have on the top, over the sxx. So to work out the least squares estimate of b, least squares because I'm squaring the difference squared and making it the minimum. So I've done both minimum. So my estimate for b is now sxy over sxx, and my estimate for a is y bar minus b x bar. So summarizing all that, in your information book you have the summary measures, and it's given at the bottom, given data, the parameters alpha and beta of the linear regression model may be estimated using the principle of least squares. So beta peak is b, the least squares estimate of the parameter b is given by sxy over sxx, and the least squares estimate alpha peak, which is our a, is given by y bar minus beta peak, the estimate x bar. So the least square regression line is given by y equals alpha peak, which is our a, plus beta peak x, beta peak is our b, and that's given to you in the information book. So we have the least squares estimate for beta is our b, which is that, and it goes through the mean, therefore that's our equation as well, and the least squares estimated for alpha is that. So those are given. A regression line can be used to estimate the value of the dependent variable for any value of the independent variable. So y would be the dependent variable and x the independent variable. Interpolation is when you estimate the value of a dependent variable within the range of the data. You're given a set of data, and if you want to work out something within that set of data, then it's called interpolation. Extrapolation is when you estimate a value outside the range of data, and values estimated by extrapolation can be unreliable, and you should not in general extrapolate, and you must view any extrapolation values with caution. So those are two bits of information you need when you're answering questions. One example, the length y centimeters of a metal rod at a temperature of x degrees centigrade is given by y equals alpha plus beta x. That's the true relationship. The length of the rod was measured at varying temperatures, and the results obtained being as shown in the following table. So the temperature was set and the length measured at each temperature. Assuming that the temperature levels are accurate and the measured lengths are subject to error, find the least squares estimate of the relationship connecting y with x. Deduce the least squares estimate of the length of the rod when the temperature is 70 degrees and the extension of the length of the rod when the temperature is increased from 70 to 100 degrees Celsius. So our summary measures, we need to sum the x, sum the y, sum the x squares, so square each one and sum them, and the x times y, so x times y and sum them. We don't need the sum of y squared this time. So our SXX is the sum of each xy minus the sum of x times the sum of y over n. So we can work those out and we get 36. Our SXX, which we need, is the sum of the x squareds minus the sum of x all squared over n, which becomes, after putting values in, 4,000. So our b we can work out first is SXY over SXX. So SXY is 36, SXX is 4,000, and we get 0.009 as our estimate for beta. B is the estimate for beta. For A, we need y bar and x bar. Well, y bar is the sum of y divided by, there's 5 there, so divide by 5, and minus b times x bar is 300 divided by 5, and we get 9.82 as our estimate for alpha. So our least squares estimate, the relationship becomes y is equal to 9.82 plus 0.009x. So that's our estimate for the linear relationship between the temperature and the length. The length of the rod, determine the least square estimate of the length of the rod when the temperature is 70. So putting it into our formula, it's called interpolation because 70 is within the range of data. So y is equal to 9.82 plus 0.009 times 70, which gives us 10.45 centimeters as the length of the rod when the temperature is 70. If we want to work out the extension in the length, the least squares estimate of this extension, we don't use that value, we use the equation for 70 and 100 and take them away. So for 100, we get a value from the equation 10.72. And then the difference between the 100 and the 70, take them away and we get 0.27 centimeters as the increase in length between those two temperatures. So once you've done your equation, you use that to estimate any lengths that you want to find. Another example, a biologist is comparing the intervals, seconds, between the mating calls of a certain species of tree frog and the surrounding temperature, T degrees Celsius. The following results were obtained. So we've got temperatures and the seconds between the mating calls. Show, and you were given some of the summary values, show that S of Tm, so you have to adapt your x and y now into T and m. So your T would be the x and the m would be the y. So show that some S of Tm is minus 90.5. Find the regression line of m on T, and then use your regression line to estimate the temperature is 10 degrees at the interval when the temperature is 10, and then comment on the reliability. So we're given some of the summary values. So we need S of Tm. Well, S of Tm would be the sum of each t times m, which we are given, minus the sum of t times the sum of n, m all over n, how many we've got. So we need to work out the sum of t and the sum of n. Therefore, adding up all the t's, we get 140. Adding up all the m's, we get 320. So our sum, our S of Tm is 469.5 minus 140 times 32 over 8. And we get minus 90.5 as suggested. So our regression line, we need our B first. So our B is the S of Tm over the S of Tt now. T is our original x. So we get minus 90.5 over 354, and we get a value for B of minus 0.2556. A goes through the mean, so the mean of m would be 32 over 8 minus, and so we need minus 0.2556 multiplied by B, or that is B, and the mean of t, which is 140 over 8. That's our x, that's our y. And we get a value for A of 8.473. So our estimate for the equation m is equal to 8.473 minus 0.2556 times t. Part C, use your regression line to estimate the time interval between mating calls when the surrounding temperature is 10 degrees Celsius. So putting 10 in there, we get a value for m as 5.92 seconds. Is this reliable or not? Well, it's within the range of data. Our 10 degrees Celsius is within this range of data, therefore it should be reliable. Last one, the weight W grams and the length L millimeters of 10 randomly selected newborn turtles are given in the table below. So there's the length and there's the weight. You may use S of LL. Our L is our X, our W is our Y. So S of LL is 33.381, S of WL is 59.99, and S of WW is 120.1. Find the equation of the regression line. Use your regression line to estimate the weight of a newborn turtle of 60, length 60 millimeters, and then comment on the reliability. Okay, so our B is S of LW over S of LL. S of LW or WL is 59.99 and S of LL is 33.381. So our estimate B for beta is 1.797. We need the mean as we're going to be working out the estimate for A. So we need to add them up so that the sum of the L's comes to 518.3. The sum of all the W's comes to 327. Therefore for A we need W bar minus B times L bar. So our W bar is our Y, so 327 divided by 10 minus our B multiplied by our L bar, which is 518.3 divided by 10, which gives us minus 60.445. Therefore, our estimate of the least squares regression line would be minus 60.445 plus 1.797 times L. Use your regression line to estimate the weight of a newborn turtle of length 60. So if you put 60 instead of L, we get a weight of 47.38 grams for this backbone turtle of length 60 millimeters. Is this reliable or not? Well, our 60 millimeters is not within the range, so we're extrapolating. We're outside the range of the data, so it may be unreliable. And that's the end of the video on regression lines.